All right, here we go. Derivative applications. We've got some basic skills down. You can deal with polynomials and e and maybe some trig at this point. We're going to see how much of that we can put together here. All right, so here we go. Let's first talk about quantities that change with time. Okay, so a couple of examples. You've got displacement, s of t, right? As time progresses, an object's position can change. Okay, so changing with time. The height of a person riding a Ferris wheel, right? You got a Ferris wheel, somebody's going from the top down to the bottom, up to the top, so the height is constantly changing, a periodic function. Now you'll notice that here on the sides it's going to be changing faster than it is on the top. In the top it may take a second to go this distance right here, which doesn't change the height very much, but in a second on the side travels a much bigger distance. So it's going faster and slower, so it doesn't have to be constant. All right, we have r of t, which is the number of rabbits in a colony. So at the beginning you got 2 rabbits, and then all of a sudden you got 6 rabbits, and then all of a sudden you got 27 rabbits, right? So you've got that changing over time as well. All right, so hopefully we can kind of make sense of some of this. And how does this affect with derivative? Well, when we take the derivative, we're looking at how that y value changes in time, right? dy, dt. How does y change over as y is changing? How is that affected by when x changes, right? So how is y being affected? So, for example, if I wanted to look at ds dt, I would be looking at the change in position over time. And change in position over time, you may be familiar with, is just velocity. Okay, you could look at something similar with dh dt. Okay, that's not necessarily velocity, though it is how is its height changing over time, which would have a lower number here at the top and a higher number here on the sides of your Ferris wheel. And same thing with the rdt. You could come up with a similar relationship there. Okay, so let's look at a couple examples. Let's just go straight into it. Right here, we got a psychologist says that the ability of a person to understand spatial concepts is given by a equals 1/3 root t. Now, if we think about this, what does this function look like? Well, it looks like this, right? That's a square root function, so square root of t. And it's a third of that, so it'll be a little bit more narrow, I guess squashed vertically, right? Compressed, from 5 until 18. So this doesn't even actually start counting until we get to 5, and then when we get to 18, it stops. Okay, now what do you notice about a person's ability to understand spatial concepts? Now, spatial concepts is like viewing things in 3 dimensions, you know, like the vector stuff. If you've done vectors, that's very spatial, being able to picture points at different places in a 3-dimensional grid. A lot of times people think of this as being the person who you want packing the car, right? Or to organize the cabinet or the dishwasher, because they can visualize spaces and where things fit and how things don't fit and that kind of stuff. That's spatial concepts. So this psychologist says that it varies with this relationship from the ages 5 to 18. And you can see that the ability, so this is A, and time. So the ability to understand spatial relationships is increasing. All right? So if we want to find the rate of an improvement in ability to understand spatial concepts, then what we need to do is to find the rate of improvement. Well, we can find the ability, right? I can find the ability at the age of 9 just by going 1/3 times the square root of 9. But what that gives me is 1/3 times 3, so it gives me 1, right? Which is the ability. I can also look at 18, and I'll get another number, right? It'll be 1/3 times the square root of 18, which I can simplify that to 3 root 2. 3 cancels out, so root 2, which is about 1.4, So obviously the ability is increasing. What do these numbers mean? Well, yeah, that's another question. But what we're looking at here is the rate of improvement. So how is that increasing? Okay, well, that is how is it changing over time. So in order to find that, we're going to need to take the derivative. So let's take A and let's find dA dt. How is A changing over time? Okay, now to do that, the easiest way is probably to rewrite this as t to the 1/2. Because if you do that, then you can bring the 1/2 in front, and so you get 1/6, and then t to the negative 1/2. All right, or in other words, 1/6 square root of t. So that's dA dt. Now, When they're 9 years old, you can put the 9 in, so you would get dA dt 1 over 6 times square root of 9, which would be 3, so that would be 1 over 18 would be the answer to letter I here. And then, oh, sorry, it should be 16. I lived at 18 before, so if I did 16 years old, I would do 1 over 6 times square root of 16, which would then be 1 over 24. So what do you see, now that we're thinking about it, what do you see about the rate of increase? Okay, we know that they are getting better at spatial relationships as they get older. That's understood. But what do you see about the rate? Well, we started off with a rate of 1 over 18, and now we've got a rate of 1 over 24. This is a smaller number. So even though the understanding is increasing, the rate of increase of that understanding is actually slowing down. Okay, and this makes sense. If you don't know anything about spatial reasoning, then anytime you learn something, you're going to be closing that gap. The more that you learn, the harder it is going to be to refine that a little bit more. Okay, diminishing returns. You'll talk about that in econ or something sometime if you haven't done it yet. But there you go. So letter B says explain why dA dt is greater than 0 between 5 and 18. Well, if you look, t is between 5 and 18, which means t will always be positive. If t is always positive, then this value will always be positive, which means that a will always be increasing. Okay? Now, if we look at C, it says explain why the second derivative is less than 0. Okay, well, if we take that derivative and we want to do d squared a over dt squared, then we just take that first derivative and we take the derivative of that, which means we take the 1/2, put it in front. So I'm going back in this. I don't have the square root on the bottom anymore. Take the 1/2 in front. That now makes it negative 1 over 12 t to the negative 3/2, or in other words, negative 1 over 12 square root of t cubed. Now again, t is positive, and because t is positive, this will be positive down here on the bottom, meaning that it will always be negative. So what is this saying? Second derivatives are harder to explain than first derivative. First derivative is just how is a changing? Well, it's changing less and less. It's still increasing, but changing less and less. Now, how about the second derivative? Well, the second derivative is now saying, okay, well, how is the change changing? Well, we saw here that the change decreased, right? The rate of increase of understanding was decreasing. Their understanding at a slower and slower rate of increase. All right? Understanding is still increasing, but it's increasing by less and less as time goes on. And that's why you have a negative second derivative. All right? And so we've talked about that. We've talked about the significance. Let's move on to another example. Sometimes it just helps to see different things. All right? But that's what we got going on. So now we got Sea Blue, which makes denim jeans. The cost model for making X pairs per day is this right here. So that's the cost. Now the first question is asking for the marginal cost. Now what is the marginal cost? The marginal cost is how much does it cost to make the next item. Okay? So sometimes it's not important how much the average cost of my items is. You know, if I'm making 1,000 items and I'm selling them for $5 each, I need to know, do I want to make 1,001 items? If it costs me an extra $10 to make that 1,001st item, that extra item, then I probably don't want to make it because it costs more or the same as what I started with, is what I'm selling it for. So the marginal cost is how much is it going to cost me to make one more pair of jeans, right? How much is it going to cost me to create one more item of whatever it is? So let's find the marginal cost. That's C prime. So we go ahead and do that. We do the derivative, which is going to lead us to C prime of x is equal to 0.0009 x squared plus 0.04x plus 4. Note that we're just using our simple power rule, bringing the 3 in front, subtracting 1 to get 2, bring the 2 in front, multiply by 2, subtract the 2 to get 1, and on the last one, 1 goes to 0, that becomes a constant, and derivative of a constant is 0. So we found the marginal cost function. So now it asks us to find the marginal cost of 220. So that means C prime of 220. And I'm going to bring up my fancy calculator here. And so I'm going to go 0.0009 times what was it, 220 squared plus 0.04 times 220 plus 4. Okay, so I get an answer of 5636. All right, now this original function was a cubic function, regardless of what it looks like, because this is going to help us kind of interpret it. So I got a cubic function here. Okay, item 220. So remember, the derivative is talking about the slope at a specific point, the rate of change at that point. So if I go out to 220, okay, that says that the slope at 220 is 5636. Okay, that means that each time I go up 1, if I were to go up and decide that I want to make 221 pairs of jeans, the price would go up by 5636. That's what slope is. Slope is rise over run, right? Y over x. So if x increases by 1, y should increase by 56.36. Now this is a continuous function, and the slope is not going to remain constant, but it does give us a good estimate of how much is it going to cost me to make that next pair of pants. Well, the next pair of pants is going to cost me $56.36. Well, how much am I selling it for? If I'm selling it for $55, then there's no point to making an extra pair of pants, because it's going to cost me more to make that one extra pair of pants. So that's what this is doing. It says, I've already got 220 pairs of pants made. How much is it going to cost me to make the 221st pair of pants? Well, one more is going to cost me $56.36. All right. Now the question says, find the minimum marginal cost for making jeans. Okay, well, minimum, easy. So how do I get a minimum? Well, I've got a function here. To get the minimum, you could plug this in a calculator. You could use your calculator function to calculate the minimum. We also know that we get a minimum. If this is my graph, the minimum is right here. But this is the minimum cost. The marginal cost would be the minimum slope. So the marginal cost, even though this is a cubic, the marginal cost is going to be a quadratic. Okay, now if the quadratic looks like this, here's my minimum. The minimum is when the derivative is 0. So the derivative of c prime, the marginal cost. So what I need to do is take the second derivative. So I go c double prime, which then is going to be 0.0018x plus 0.04. And at this point, I'm going to set that equal to 0. All right. And if I solve for that, then I'm going to end up getting a negative number, which doesn't help me at all. Oh, sorry, there's the calculator. There we go. And so I subtract the 0.04, so 0.04, and that's now going to be negative, because I subtract it to the other side. And then I'm going to divide by 0.0018. And I get negative 22. So the minimum marginal cost, what that means is that this hump actually happens before 0, which means the minimum marginal cost is going to be right there at my y-intercept. Okay? Because that is this one, so my marginal cost will continue to increase. So the minimum marginal cost, realistically, is going to be when I get to 0, because this right here is at negative 22 point, whatever that decimal was. So at 0, I can go ahead and put 0 back into my original function now. And so I should then be able to get, or sorry, back into this one, and I should be able to get the minimal marginal cost, which is then 4. Okie doke. Hopefully that makes sense. Hopefully that kind of works out. Let's look at another one. Let's do some trig, eh? Find the rate of change in the area of triangle ABC as theta changes at the time when theta equals 60. Okay, well, how do I get area? Area of a triangle equals 1/2 AB sine C, right? Okay, well, I've got A and B, got sine C, so if I call this A B, C, so sine capital C is the one opposite side C, so that's that one right there. So area here is equal to 1/2 times A, which would be 12, times B, which would be 10, times sine of C. Now these are constants, those are not changing. The angle right here can change. So even though it's sine C, it's actually at point A here. Okay. Now I need to take the derivative of that, right? And so we're going to take the derivative because I'm finding the rate of change in the area. So the rate of change in the area would be dA dt. Sorry, not dt, as the angle changes. So as the angle changes, we'll go 1/2 times 12, which would be 6, so 60. And then the derivative of sine is cosine. Right? So there you go. We got 60 cosine C. And we can go ahead and finalize because this actually asks for specifically at the time when theta equals 60 degrees. So dA d theta is 60 cosine of 60, and we can get cosine of 60 because if this is 60, the way that I like doing it is if this is 60, then I got 1, 2, root 3, and cosine would be adjacent over hypotenuse. So dA d theta equals 60 times 1/2 adjacent over hypotenuse, which is then 30. So 30 dA, so A is centimeters squared, divided by degrees, d theta. That's the number of degrees that are changed. So that's the rate, 30 centimeters squared per degree. All right, and that's the answer to the question. Let's do one more. Why not? Let's throw in something with E, right? Okay, so for the function f of x equals e to the ax times x plus 1, show that the first derivative is, and then we got some fun. So to get the first derivative, obviously this is going to need a chain rule, so I got e to the ax, not chain rule, x plus 1, product rule. Okay, so u equals e to the ax, and du then is e to the ax times a. All right, and then we've got v, which is x plus 1, and dv, which of course would just be 1 then. Your other options, you can distribute this, and then you can take care of it that way as well. So we've got f prime of x, which is going to be equal to e to the ax times 1 plus ae to the ax times x plus 1. And so now all we have to do is simplify. So we're going to factor out the e to the ax. This will leave us with 1 plus a times x plus 1, which is what we have right there, just the ones in a different order. All right, so we got the first derivative. Very nice, very nice. All right, moving on. Show that the second derivative equals this. So again, we're going to take the second derivative. All right, so we take the second derivative, and again, you can do it either way. I'm going to go ahead and do the product rule again. So if u equals e to the ax, du equals a e to the ax, which is easy because I already did that. V equals 1 plus a times x plus 1. So therefore, dv equals the derivative of this. So derivative of 1 is 0. A to the x plus a would be another constant. So it's the derivative really of a to the x, which is a. And so then I can go that the second derivative is equal to u times dv plus v times du. All right, and we can go ahead and solve that. Just we can simplify it again. They want us to factor out the a e to the ax, which would then be 1 plus 1 plus a x plus 1 And you can then see that it matches this one right here. 2 plus a to the x plus 1. All right, so there you go. Now, it then says if k to the x equals a times k minus 1 e a to the x, a x plus 1 plus k, then f k plus 1 of x equals a to the k e to the ax, parentheses a x plus 1 plus k plus 1. All right, well, very good. Let's see if we can figure that out. So this is a more mathematical idea. So we're going to go ahead and erase everything that we got so that we got a little bit more space. So if we have a specific derivative that is a to the k minus 1 e to the ax times a times x plus 1 plus k, we want to show that this will give us that one right there. So if this is the kth derivative, then let's do the next derivative. So again, we can use the product rule. If you want to distribute, you can. I like the product rule, so we're going to stick with that. So we're going to say that u equals a to the k minus 1 e to the ax. That means the derivative of u. All right, now a to the k minus 1 is a constant. So really, it's just e to the ax. So du is going to be a to the k minus 1 times a times e to the ax, right? Because this is a constant, so it just stays there. The derivative of e to the ax, we've talked about before, is a e to the ax. All right, v is a times x plus 1 plus k. So dv equals, the k is going to go away because it's constant, derivative of a times x plus 1. If you distribute the a times x plus 1, you're going to have ax plus a. Again, the a is a constant. Derivative of a to the x is a. So if I put all that together, I'm going to have f to the k plus 1 of x equals u, so a to the k minus 1 e to the ax, times dv, which is a, and then plus v, which is a x plus 1 plus k, all times du, which is a to the k minus 1 a e to the ax. Let's go ahead and do all this. So we're going to finish it up. Hopefully in this step, we'll see. If not, I'm out of space. So a to the k minus 1 times a would just add another exponent because it's a to the 1. Add those two together and you get a to the k. So I got a to the k and e to the a to the x, which we're going to go ahead and take out, leaving us with a 1. Okay, down here, we're going to have a similar thing. A to the k plus 1a, right, is going to be a to the k, so that's going to come out. E to the ax is going to come out, and so that's all going to come out. So I'm going to be left with a times x plus 1 plus k, which then is exactly what we've got right there. The only difference is that they've got the k over on, or the 1 over on the other side with the k. All right, so we've managed to prove letter C. And you know what? I think that's enough for today. So watch the next video if you want to see a few more examples.